it gives me pleasure to introduce my colleague, Professor Sridhar Balasubramanian. He's an associate professor in our department, mechanical engineering department at IIT Bombay, and he's also an adjunct faculty in IDP Climate Studies. So that's the interdisciplinary program in climate studies at IIT Bombay, and he has various research interests, among which primary geophysical flows and geophysical fluid mechanics, particle laden flows, and measurement and experimental techniques. So with that short introduction, Sridhar, the online floor is yours.
Yeah, okay. Yeah, thanks a lot, Abhishek, and thanks a lot, Professor Mahendra Verma, for giving this opportunity to present our work. It's indeed an honor to be on this platform. So today I'll be talking about energetics and mixing efficiency in gravity currents. So you can see that I have put up a very short movie where you can see a gravity current is flowing from right to left. So the red is basically the denser fluid, and blue is the lighter fluid. So you can see that it is propagating, the denser fluid is propagating as a gravity current in the lighter fluid. So before I go into the successive slides, I would like to say that this work, the chunk of this work was done by my PhD student, Partha Mukherjee. He spent a good 3-4 years trying to read up this topic and trying to come up with some interesting findings. So all the credit should go to him, and I'm just presenting the work, whatever he has done, with some enhancements from my side, that's all. So with that, I will go into the details of this talk. So this is just a very basic slide on what is a gravity current. I'm pretty sure this community knows what is a gravity current, but I'll just very quickly define what it is and why is it important for us to study this. So a gravity current is a flow of heavier fluid into a lighter fluid, and it is driven by the density difference that is present between the two fluids. So again, you're seeing the same movie here. So this configuration is a lock exchange configuration, where what you have is you have a denser fluid locked in a compartment, and you have a lighter fluid in the other side. And when you release the lock, then this particular flow traverses. And as you can see, the small instabilities kick in and they mix the two fluids. So why is this important? It has a lot of applications in atmospheric as well as oceanic flows. But coming to atmospheric flows, one of the common examples of a gravity current is flow of when a cold air undercuts a warm air. Then you have the generation of a gravity current which moves downslope along a mountain or even on a flat terrain. And one of the interesting aspects is when a cold air which is dry and moist air warm air which is moist, then you would like to see how much they mix, so that you can then kind of understand what kind of vertical advection will take place and whether a cloud formation is possible or not. That is the overarching application. But leaving the thermodynamics aside right now, there is so we are only interested in the fluid mechanics aspect, wherein we want to study how much these two fluids mix. Can we quantify the mixing that happens in this kind of a configuration? And when we are talking about gravity currents, you have three distinct zones, which is the front of the gravity current. Then you have the head, which follows after the front, and then you have the body or the tail, which is the least energetic portion of the gravity current.
Sridhar, I have one question. I have a simple question.
Yeah. Yes.
So
yes.
why is heavy fluid going one way, or why is there a current? It's not a buoyancy, no, because it's a horizontal motion. So what is causing it?
So it is the potential energy that is present initially. So you have a heavier fluid which is locked in up to some depth h, and then you instantaneously release the lock, so it generates a kinetic energy. And since there is a loss of mass, so as this fluid moves towards the right, there has to be fluid which has to move towards the left to kind of take care of the mass loss, and that's how you actually create the shear. So the shear is generated automatically through this configuration.
I see. Okay. So heavy fluid has to have some higher potential energy. I mean, taller than.
Okay. Right. Absolutely. Absolutely. Right.
Okay. Thanks.
And if you look at a gravity current, it has three different phases. One is the slumping phase, which is where the inertia is very dominant. And then you have the inertia buoyancy phase, where inertia and buoyancy balance each other. And then you have the viscous phase of the gravity current, wherein not much action is happening. So whatever I'm going to present today is only in the slumping phase, which is the most energetic phase of the gravity current, which lasts for around 20 to 30 seconds in this particular flow configuration. So now going into a little bit of qualitative analysis. So the way we generate this gravity current is, like I said, it's through the potential energy of the denser fluid. So then you can actually write a Reynolds number of the flow where the velocity is given by the gravitational potential that is present in that particular system. And the h, small h here is the height of the gravity current itself, and nu is the viscosity. So by varying either the initial height of the lock, or by varying the initial gravity density difference that is present between the two fluids, you can actually generate a range of Reynolds number. And as you can see, if you generate a range of Reynolds number, then at a very low Reynolds number, you will not get too much mixing. So the dynamics are mostly governed by something known as combo waves, which are just interfacial waves, which don't allow too much mixing of the two fluids. Whereas as you crank up the Reynolds number, then you start getting the Kelvin-Helmholtz instabilities. And then finally, when you go to very high Reynolds number, then you get these billows, the Kelvin-Helmholtz billows, where there is secondary mixing overriding the primary KH role that is present. But this is the Reynolds number is an extrinsic parameter which is known to us. But in order to govern the mixing, or in order to quantify the mixing, we resort to two basic parameters that are usually used in stratified shear flows, which is the Richardson number. Here it is a gradient Richardson number because it is n squared by the shear square. Or you can use the buoyancy Reynolds number, also known as the Gibson number, which is the ratio of the viscous dissipation to some sort of a buoyancy present in the flow. So both of these are commonly used. I will, as the talk progresses, you will see how I'm going to use these two numbers. But overall, the Reynolds number only has a use in trying to qualitatively tell where you are. But in order to quantify, we will stick to Ri or Reb. So in order to quantify, we invoke the TK budget equation, where you have the unsteady term of the kinetic energy, and then you have the transport term, the dissipation term here, then the production, the shear production, and this is the buoyancy production. So this is purely due to the kinetic energy or the shear, and this is due to the potential, the buoyancy due to the stratification. Okay. So if it is a homogeneous and stratified and stationary flow, then your unsteady and transport term becomes 0. So then you only have a balance between the dissipation, production, and buoyancy. So that is helpful because then you can now define some kind of a mixing efficiency, which is a term which is used to characterize the mixing in these kind of shear stratified flows. And that definition of mixing efficiency goes like this. So there are three ways to define the mixing efficiency, also known as the Flux Richardson number. So this RIF is what is used to quantify how much mixing has occurred between the two fluids. And the very basic definition of this is, if you want me to phrase it in phrase, if you want me to put it in a phrase, then it is basically how much amount of kinetic energy has gotten converted into potential energy. So what is the efficiency at which your kinetic energy is getting converted into potential energy? So that is what this RIF basically represents. So if RIF is very small, that means a small portion of your kinetic energy is going into buoyancy. Whereas if it's very large, then a lot of potential energy is going into, a lot of kinetic energy is going into buoyancy. Okay. So if you use the stationary and homogeneous approximation, then you get the first definition of mixing efficiency, which is basically B by P. So this is very similar to what we talk about Flux Richardson number in stratified shear flows. There is not, so people have different ways of use. I mean, the terminologies are very different, but at the heart, the definition is the same in the sense that it is the ratio of the buoyancy to the production. So either you can call it the Flux Richardson number or mixing efficiency. Both are the same. However, the stationary and homogeneous assumption is not true in most of the cases. Therefore, a more generalized definition is now the second definition of mixing efficiency, which allows me to get rid of this assumption of stationary and homogeneity. And I define it further as B, which is the buoyancy, divided by all the other terms that are present in the turbulent kinetic energy equation, which is the unsteady term plus the transport term plus the production term. And this basically gives me B by B plus C. So B is the buoyancy flux and epsilon is the viscous dissipation. So if I'm trying to study this flow from a experimental point of view, then I need to measure buoyancy and I need to measure dissipation to actually get the flux Richardson number, okay, or the mixing efficiency in the flow. So, so that's what we are doing in this study. So as you will see in the later slides, we are characterizing all of these terms to actually quantify the mixing efficiency. So these are the first two definitions. There is one more definition which is most accurate, but it's slightly tricky because it also invokes the concept of background potential energy, which I will talk about detail in the upcoming slides. So just please hold on. But the overall idea of this presenting this slide was to show that there are three different ways in which you can actually measure your mixing efficiency. But out of these three, this first definition is not very useful. Second definition and the third definition, which I will invoke later, are most useful. And we are going to see what are the limitations of each of these definitions. So the next question automatically that comes up is, why do we need to measure this mixing efficiency? What is the reason? The main reason is to quantify the eddy diffusivities of scalar as well as eddy diffusivities of momentum, because it's very difficult to measure the turbulent fluxes in field scenario or in realistic scenarios. Hence, we resort to a parameterization. And when you want to parameterize these eddy diffusivities, then there is this RIF that goes into the equation. So unless you know what is this RIF value, you will not get a good, your models will not be able to quantify the diffusivity values. Okay. So over the years, starting from 1980 or even 1957, this has been a topic of huge interest since early 1950s, but even today it has a lot of ambiguities associated with it. So what independently, the three studies that was done, experimental, theoretical, and field study, it was argued that RIF, which is the flux Richardson number or the mixing efficiency, has a universal value of 0.17, irrespective of whatever stratified shear flow you are dealing with. But recently, say after 2010, a lot of people have argued that no, that's not the case. There are a lot of inconsistencies in this value. So let us see if we can understand and rectify this particular value of RIF. So that is why we are performing this particular study, and we got some interesting results which I'm going to share. So one of the reasons why this RIF 0.7 is not a universal value is because of the presence of counter gradient flux. So before I go ahead, I will say what is counter gradient flux. Counter gradient flux is nothing but you take a denser parcel and you move it up into a lighter fluid, then it will its role is to automatically come back down without mixing. So it is an adiabatic and reversible process which will just come back down, or you take a lighter parcel and move it down, it will automatically come back up. Okay. So what is the issue is that the second definition of, or the first and the second definitions of mixing efficiencies, they have this issue of counter gradient flux where they say that even if my my denser parcel is moving up, it will get mixed into that ambient and thereby giving you a wrong value of mixing efficiency. Okay, that's why there is a need for the third definition, which rectifies that particular counter gradient flux issue. Okay, so that was kind of pointed out for the first time in this 2016 paper by Venayagamurthy and Kosef, that they said that, okay, I will do a DNS study. So this is the DNS data for stably stratified turbulence. So what they did is they did a bunch of experiments, DNS experiments, where they fix. So let us say you fix this RIG, the gradient Richardson number of 0.6. And there are multiple ways to get this 0.6 value by changing n square and s square appropriately. So I can change n square to some value, I can change h square to some value, but I can still get the same value of 0.6. So if you look at 0.6, then you can see that there is no convergence at all. So the cross is RIF, the first definition. The circle is which is in blue, is the second definition. Both of these definitions has a lot of divergence. So they are not showing any universal nature as such of mixing efficiency. It is all over the place. Okay. But then when I have not introduced the third definition yet, but which I will do right now. But the third definition of mixing efficiency, which accounts for only the irreversible mixing that is happening, which doesn't account for the reversible processes, that showed a lot of promise, and that kind of showed some kind of a convergence where you say that, okay, some kind of universal mixing efficiency value is being achieved. But the issue with this study was it is a very simplistic, homogeneous, isotropic, stably stratified turbulence, which is not very, which is the most simplest way of looking at the at this particular flow. Okay, it may not be applicable for a gravity current, which we are talking about. Okay. So I have already explained what is this counter gradient flux. So the definitions of mixing efficiency that we have so far, they don't distinguish between the irreversible and the reversible buoyancy fluxes. Hence, there is a need to rephrase this mixing efficiency in a better fashion, which brings us to the third definition, which is based on the potential energy in the system. So let me kind of walk you through these two slides. So that if you have this is my gravity current system where I have the denser fluid on the right-hand side and I have the lighter fluid on the left-hand side. So this is the initial configuration. So in this initial configuration, I will have some gravitational potential energy which is present in the system, which can be given by your normal potential energy formula. And then so this is not our work. This has been taken from a 1995 papers by Winters et al. What they said was, you take this configuration and do a cross sorting. When you cross sort, basically put the layers in a horizontal manner, and that will be the least amount of energy. This is the least energy system that this particular configuration can reach. Okay, this is the least energetic system that this particular configuration can reach. So find out the background potential energy of the system of the initial configuration. The difference between the potential energy and the background potential energy will give you something known as available potential energy, which is available for mixing. So this is the total energy now that is available with me for mixing after doing this cross sorting. Okay, this is again the initial. So this is the initial amount of energy that is available to me for mixing. And then you let the gravity current run. So you let the gravity current generate and let it go from right to left, or whichever direction it is, and let it come to a steady state, or let it come to a no motion state. Once all the motion has ceased, then you can actually find one more state of background potential energy, which is the final state. Okay, after all the mixing has occurred. So then they said that the mixing efficiency can be defined as the background potential energy in the final to the background potential energy in the initial state divided by the available energy in the initial available energy in the system. So what happens here is, once your energy has gone into creating that background, then you don't have any reversible fluxes. Everything is irreversible because that energy has already been spent into creating that background. Correct? So they said this kind of definition will only account for irreversible mixing. And this is a much more accurate depiction of your mixing efficiency, and hence this is what should be used. Okay. Then there is one more thing. The limitation of this particular formula is that you should wait for the initial and final states. In between, so it's more like an integral approach where you can't say, okay, what is happening in between. So then there was a differential approach where they said, okay, let us now convert it into a differential approach, because as the flow is evolving, can we measure the mixing efficiency at every time step? Okay, because that's what I want. I don't want just the initial and final, and I don't want an integrated value, because that integrated value is accounting for the slumping phase of the current, the inertia buoyancy phase of the current, and the viscous phase of the current. So everything is kind of now clubbed into one. Whereas I want to know how much mixing is happening during the slumping phase, which is the most energetic phase of the current. So then in that case, there was that you can set up an equation for potential energy and the background potential energy. And since I'm interested in the background potential energy of the system, so you have advection term and you have the molecular diffusion term. And there is this one term which is very important. And this particular term is this is the eddy diffusion term. And this is what actually gives rise to your definition of mixing efficiency, which is the third definition. Okay, I would not go into detail because it is very well explained in the papers. Like I said, this is not our work. I'm just putting a framework together here. That's all. So the third definition, which only accounts for the irreversible fluxes, is now given by the rate of change of the background potential energy to the total energy, which is the sum of potential plus kinetic. Okay, because that is the total energy that can come from potential as well as kinetic. So this is, in some sense, this is the dissipation due to, this is the viscous dissipation. This is the viscous dissipation due to the potential energy present in the flow. So that's another way to look at it. But this is the most accurate form. Okay. So after kind of putting together this framework, we decided, okay, let us do experiments and try to see if it is indeed the case for a gravity current where you do see counter gradient fluxes when you use the first two definitions, and the third definition actually gets rid of it. So that was our first kind of a validation that we wanted to do with experiment, because nobody has experimentally done this yet. That's what we found out. Like DNS studies has been done, but experimentally it has not been done. So we set up a lock exchange system where we put a denser current here, denser fluid here, and we put a lighter fluid here. And for we did experiments for a different range of Reynolds numbers, starting from 485 all the way to 12,000. So we did 12 experiments, and this is just a representative of how the gravity currents look, how the gravity current looks. And we have kind of stitched different images. We use laser to illuminate one particular portion and two cameras. One camera is a PIV camera, which measures the velocity. Other camera is the PLIF camera, which measures the density in the flow. So then you can simultaneously, and the good thing is it measures it simultaneously, so that you can actually simultaneously get the velocity and density fluctuation, so that you can calculate the scalar fluxes as well as the momentum fluxes. More details are available in our paper because this has been published in Physics of Fluids as well as PRF as well. So if you want, I can share more details, but in the essence of time, I will not talk too much about the experimental setup right now.
Just one question. Go
Yes.
back. So the red region is in the left, no? In the bottom figure.
Yes, here.
Bottom figure.
Yeah. So this particular, so when you start this particular system, this red portion starts moving.
So that is in the bottom figure is in the left, right? Is that correct? Or right? Where is it? Should be in the left, no?
Bottom figure. So can you say that again, Professor Verma? I didn't understand.
The red block, heavy block, should be in the left. So the head is bigger.
Yeah. So no. This is in the right initially. So this entire fluid is kind of pumped. I mean, it is kind of sitting here, and then when you release the lock, so there is a lock here. So when you release the lock, the head forms here, and then it starts moving downstream.
I see. So it's like a full bulk moving.
Yeah. So this full bulk moves because unless and until you reach a state where all the energy has been spent, this will not come to a kind of a no motion state. So this height, one of the parameters that defines how much energy is present is how much is the height of this denser fluid.
And the height of the head will keep going down as with time. Is that correct?
Yes, right. The height of the head will keep going down, right? So it's a transient system, basically.
Okay.
Right.
Okay, thanks. Continue, Sridhar.
So first thing that we wanted to check was whether you are seeing hobo waves, KH instability, and stronger KH instability, which are causing the spikes in between the two fluids. And we actually were able to capture it. So these are quite high resolution. I would say the vector resolution of PIV was around 1.5 millimeter per vector, and similar was the case for the PLIF as well. Like density also, we were able to get similar kind of resolution. So these are quite high resolution images, and you can clearly see hobo waves, KH, and stronger KH. And that is also visible in this the kinetic and turbulent kinetic energy plot, where you can see initially the energy is very high and then it kind of decays down because the head is reducing and your energy that is present keeps reducing. So it's a decaying turbulence. basically. So it's not like the DNS, where DNS the turbulence was sustaining, whereas here it's a decaying turbulence. So like I said, in order to quantify the mixing efficiency, you have to be able to measure the production, the buoyancy, and the dissipation, all three of them. So we were able to measure these things with time as well as in space. So this is the integrated production, buoyancy, and dissipation as the current moves. So you can see that it reduces as expected because the energy is reducing. And at one specific location, if you plot the vertical profiles, then you can see that the production is very dominating. Like the production has the most dominant values. And of course, since the production is higher, buoyancy is also higher. Dissipation is also higher. And you can see that in the Hombo wave, buoyancy is not having any role to play. Like it's very small. Whereas the buoyancy kind of keeps increasing as you go to higher Reynolds numbers, because the amount of energy that is being converted. So the mixing efficiency keeps increasing. That is qualitatively, we can tell that. So then we also try to take a look at the Kolmogorov scale. And so we were able to resolve the Kolmogorov scale because our lens scale, our resolution was 3 times more than the Kolmogorov scale. So if your resolution is within 5 times the Kolmogorov scale, then actually dissipation can be measured. 90% of the dissipation can be estimated. That is what the previous research papers have told us. So we wanted to keep our resolution very close to the Kolmogorov lens scale, but we couldn't keep it very close. I mean, we couldn't keep it exactly at the Kolmogorov, but it was 3 times more, as you can see. Okay. And Osmedov lens scale is basically the smallest lens scale at which the buoyancy effects will be visible to you. So that is the importance of Osmedov lens scale. So we plotted them to see what kind of scale separation we are getting, and we are seeing that at very low Reynolds number, it is nearly homogeneous and stationary. But as you go to higher Reynolds numbers, then you actually see a scale separation between Osmedov and Kolmogorov lens scale. But this is the most important aspect of our study, where we actually were able to experimentally measure all 3 values of Flux-Richardson number or the mixing efficiency. And this is exactly what I'm talking about. This is the issue, the counter gradient flux. As you can see, the values become negative. So as the values become negative, then this is basically due to the counter gradient flux, because your buoyancy becomes negative, right? Because according to the counter gradient flux theory, whatever is moving up should come down. But if it has already mixed, then the system is seeing it as an unstable buoyancy flux, and that's why it is giving it a negative value. Okay, and the amount the counter gradient flux effect decreases. It doesn't mean that it is going away, but it decreases as you go to higher and higher values of buoyancy Reynolds number. The reason is because as your buoyancy Reynolds number increases, then your inertia also increases, and because of that, even if you put a denser fluid up you take the denser fluid up to a lighter the lighter fluid, then what may happen is the inertia will kind of help in mixing a little bit. Okay, so that's why as you keep going away to higher and higher REB, the impact of counter gradient flux reduces to some extent, but it doesn't go away totally. And that is very clear from the values of mixing efficiency. So if you see, the plateauing value of this mixing efficiency is around 0.15. The second definition is around 0.2. But the third definition is 0.12, which clearly shows that this has accounted for some additional mixing, which was the reversible mixing, which shouldn't have happened in the first place. So we are overestimating the values of mixing. And that is one of the issues in most of the models, where if you are overestimating the mixing, you are overestimating your diffusivity values. Okay, so a right value of RIF star or a right value of mixing efficiency is needed to kind of give accurate values of your diffusivities. That is one thing, and that was the first step towards. I mean, that kind of showed up in our result that okay, this is almost 2 times. So 0.2 versus 0.12. Okay, so if you only consider the irreversible mixing, then your mixing efficiency values are going to be very different, which is RIF star. Okay, so we were confident that RIF star actually gives the most accurate representation of mixing, as kind of told by DNS study, which was not for this kind of a flow. Okay, so because that was for a very simple flow, we kind of extended it for a slightly more complex flow. And then we went on to actually characterize the diffusivities of momentum and scalar. And we found out that interestingly, so this was calculated. This was calculated using RIF star. So the third definition, because that is the most accurate. So we use the third definition to calculate the eddy diffusivities. And we saw that for the eddy diffusivity of momentum has a very nice parameterization, which even which stays kind of which gives a good fit even at higher values of buoyancy Reynolds number. But when you come to the eddy diffusivity of scalar, then your this 0.2 REB, which has been used in traditional models, it breaks down. And it only works up to intermediate regimes of REB, and it doesn't work in the higher values. So this kind of so our conclusion was that there is a need to relook into the parameterizations that are being used in the models from a viewpoint of, especially for a scalar diffusivities. So this is one issue. Then we dig a little bit deeper, and we found out that there is another issue which is related to the non-universal nature of the flux Richardson number or the mixing efficiency. So as you can see, we are now sticking to the third definition because we know that that is accurate. But the issue is that even after getting rid of the the counter gradient flux, we scoured some literature and we found out that if you, depending on the regime in which you are in, if you're in the shear dominated zone, if you're in the inertia dominated zone, or if you're in the buoyancy dominated zone, so that means if you are in the weak stratification, strong turbulence zone, or if you are in the strong stratification, weak turbulence zone, that can also have a very huge impact on RIF star or the mixing efficiency. So clearly the RIF star value of 0.17, which was proposed by Osborne, is complete. I mean, it's not at all valid because there are a lot of inconsistencies there, because you first need to see which regime you are in. Okay. Because it's all over the place. The values get all over the place, right? So then we asked the question, can we simply use just one definition of non-dimensional number, which is Ri or REB? Okay, and could we kind of separate out the regimes? Okay, so the answer is no. So basically, to kind of put it in perspective, if you take REB, the value of REB can be obtained, the same value of REB can be obtained either by changing the dissipation to a very high value or changing the stratification to a very low value. Okay, and that can give a very different zone. That can have a very different, you can be in a very different parameter zone, sorry. Okay, so you can either be in a strong stratification, strong turbulence zone, or you can be in a weak stratification, strong turbulence zone. Okay, so the DNS studies have found out that most of the time when you are only sticking to a single parameter like Ri or REB to quantify the mixing efficiency, then you are only in the weak stratification, strong turbulence regime. You are never in the strong stratification, strong turbulence regime. It's very difficult to get this. Okay, so then we kind of said, okay, how can we distinguish this parameter space? Okay, so the answer is you have to kind of split this REB into two different non-dimensional numbers, just like what we do. Like so we say that your Rayleigh number is Grashof into Prandtl, right? Very similarly, you have to kind of split this REB or Ri into two separate non-dimensional numbers, and that's what we decided to do using the framework of a paper that was published in 2014. So they said that let us define 4 different variables. The N is your buoyancy frequency, S is your shear. And apart from these two, we will define 2 time scales. One is the time scale at which your energy is going down to dissipation. And the next one is the Kolmogorov time scale. So this is more like a eddy kinetic energy time scale, and this is your Kolmogorov time scale. So when you put all of these together, then what you can actually do is you can come up with 4 different non-dimensional numbers. Okay, one is your buoyancy strength, which is NTL, which can also be written like this. Other is the turbulent fluid number, then the shear strength, and the turbulent Reynolds number. And all of these are turbulent quantities because they depend on your U prime. your fluctuating terms, right? So that is very important. And then when you define this FRK and REL, when you introduce these two, turbulent fluid number and turbulent Reynolds number, then you can see that you can actually split this REB into FRK square into REL. So you can actually get this REB as a function of two different non-dimensional numbers. And similarly, you can get RIG also as a function of two different non-dimensional numbers, which is the buoyancy strength to the shear strength. This is what we found out. So now we decided, okay, let us now, whatever data we have, let us now try to put it on this parameter space. And we found a very interesting result, which we didn't expect. So this is the plot that I already showed you, RIF star. Okay. So we said, okay, each RIF star, we will take it and we will now translate it into this parameter space, which is a parameter space which contains FRK on the y-axis and REL on the x-axis. And these are iso REB lines, in the sense that these are the lines which have the same buoyancy Reynolds number values. So what we found out was that if you, let us say you take you have the same buoyancy Reynolds number, let us say REB 100. Depending on FRK and REL, you can be in the strong stratification, strong turbulence regime, or you can be in the weak stratification, strong turbulence regime, or laminar regime. So there is no, just by using a single REB value, there is no, you don't know where you are on this parameter space, whether you are in the laminar zone, or whether you are in the weak stratification, strong turbulence zone, or you are in the strong stratification, strong turbulence zone. And it's very important to know, because this is what is going to trigger what kind of RIF parameterization you should use. Because like I said, since people were kind of, like this idea was there that RIF is universal. So people would just use one value irrespective of what kind of regime they were in. But it's not true, because your RIF value is heavily dominated by which regime you are in. And just by using single REB value, you cannot decide that. So whatever we are plotting here, this is not enough. This is not at all enough. You have to now translate this into a different parameter space and then see where you are in, and you have to come up with a separate parameterizations for strong turbulence, strong stratification, weak turbulence, strong stratification, weak stratification, strong turbulence, and each of these regimes. Then only you will actually get a very good representation of the mixing efficiency in stratified shear flux. And lastly, we did the same thing for RIG as well, because either RIF star is characterized with RIG or REB. Both of these non-dimensional numbers are used. So the same thing we found out when we put it on a NTL STL map. Then we found out that there is a buoyancy dominated regime, there is a shear dominated regime, and there is an inertia dominated regime, and your RIG cuts across both of these regimes. So depending on whether RIG is 0.6, so the value, that's why you see a lot of scatter, because the scatter that I showed in the earlier plots was because they didn't, for the same value of RIG, you can get multiple values of RIF star, right? But you may be in a very completely different regime. So either you are in a buoyancy dominated regime or you are in an inertia dominated regime. So depending on which regime you are in, you will actually get that particular value of mixing efficiency. So it does, whatever has been proposed in the literature makes sense. Like RIF is not a universal value. What we did was we kind of gave it a much more, we try to put it in a different platform to improve our understanding of what exactly is happening with this mixing efficiency. And we showed that, yeah, this RIF star, the counter gradient flux is one issue. But even after you get rid of that counter gradient flux issue, you still have this other issue where you need to see which regime you are in, so that you have to use that particular value of mixing efficiency. So with that, I would like to conclude. And just to summarize that Hombo waves and Kelvin-Helmholtz instability are the dominant modes through which the mixing occurs at low and high Reynolds number respectively. We try to use all the three definitions of mixing efficiency that has been available in the literature, and we found out that the plateau or the constant value of this mixing efficiency is 0.15, 0.20, and 0.12 respectively. And we realized why this 0.12 is the most accurate representation, because it accounts only for the irreversible flux. Additivity of momentum was well represented, but scalar needs, the parameterization needs to be improved. And finally, we propose that the dual nature of non-dimensional parameters that are being used, which is RIG and REB, buoyancy Reynolds number and gradient Richardson number, they need to be, that is not enough to completely tell the story. We need to actually put it on a parameter space and then go ahead and try to quantify the RIF star depending on which region, which regime we are in. Okay. So with this, I would like to conclude, and I once again thank the committee, the members of this seminar group for giving me an opportunity, and I'll be happy to take up any questions from the audience.
Thanks, Sridhar, for exciting talk.